Hello students, welcome to Time Classes. I hope you are doing well. This session is part 1 of the third session on permutation and combination. In this session we are going to first look at a few questions on selection, and then we will look at the concept of how to find the number of ways or number of routes from one point to some other point. And we will also look at the concept of something known as derangements. Fine. So we will continue with the same handouts we have been using for this topic, which is QAHO 1002127 and 212A. So let's begin with the session. So let's look at this question from your sheet. This is additional question from QAHO 2127, question number 3. This question says there is a question paper which contains 3 sections and each section contains 6 questions. So in how many ways can a student attempt 13 questions such that he attempts at least 4 questions from each section? Okay. So he has to attempt 13 questions in all, and there are 3 sections containing 6 questions each, and there is a condition that he has to attempt at least 4 questions from each section. So let us first look at what are the possibilities. Okay, so these are the possibilities. So let's name the section as section A, B and C, and there are 6 questions in each section. 6 questions, 6 questions, 6 questions. So if he has to attempt at least 4 questions from each section, let's start with that minimum quantity. So it is possible that he is attempting 4 questions from section A, 4 from section B and 5 from section C. So start with the minimum number of questions from any section. So if you take section A, in that he attempts 4, then in section B he will attempt 4, and let us say section C he will attempt 5, because total has to be 13 questions, right? So 4 plus 4, 8 plus 5, 13. So the combination for attempting the question will remain 4 questions and 5 questions, right? Because he has to attempt at least 4 questions. So that means he will be attempting 4 questions from 2 sections and 5 questions from the other section which is left over. So this is one possibility. So there are 6 questions in every section. So number of ways of selecting 4 questions from section A is 6C4, 4 questions from section B is 6C4, and 5 questions from section C is 6C5. Okay. Similarly, he can attempt 4 questions from here, 4 questions from here, and 5 questions from the middle section. Okay. The number of ways is 6C4 into 6C5 into 6C4. Or he can attempt 4 questions from section B, 4 from section C and 5 from section A. In this case, from the first section number of ways is 6C5, then 6C4, then 6C4. So if you see, this product and this product contain the same quantities multiplied together, only the order is different. But since you are multiplying 3 quantities in each of these and they are the same quantities, only the order is changing, so product is going to be the same, right? So this product is going to be 1350, and therefore this is also going to be 1350, this is also going to be 1350. So total number of ways will be 1350 plus 1350 plus 1350, because these are 3 different possible cases. So just add the total number of ways of all the 3 cases. So if we add these 3 together, we'll get 4050. This is the total number of ways in which he can attempt the question paper. Fine. I hope it is clear. Fine. Let us move on to next question. So this is question number 11 from sheet number 2128. It says there are 7 reasoning books, 6 quant books and 5 English books in a shelf. In how many ways can a person select at least 1 book? Now see, if the question does not specify whether the books are identical or not, so it is just saying 7 reasoning books. So if nothing is specified, then we consider the things as distinct or different. So these are 7 different reasoning books, these are 6 different quant books, and these are 5 different English books. Okay. If the books are going to be identical, it will be mentioned in the question. If nothing is mentioned, then by default we'll consider the things as different. Okay. So all these books are different. So first case is, in how many ways can a person select? First part is at least one book. So there are 18 different books in total. 7 plus 6 plus 5. Those are 18 books and all of them are different. So there are 2 choices for each book. We will select the book or not select the book. Right? We have done such cases earlier also. So every book has 2 choices. It will be selected or it will not be selected. So first book has 2 choices, second book has 2 choices, third book has 2 choices, and so on till the 18th book. All of these books have 2 choices each. So what is the total number of ways? 2 into 2 into 2 multiplied how many times? 18 times. So total number of ways of selecting the books will be 2 to the power 18. And this also includes one way where we are not selecting any of the books, right? This 2 to the power 18 also contains a way where first book was also not selected, second was also not selected, third was also not selected, and so on. So if none of the books are selected, that means there is only one way of not selecting any of the books. But what does the question say? The question says that he has to select at least one book. So hence number of ways of selecting at least one book will be 2 to the power 18 minus 1. Right? This one way in which we are not selecting any of the books, that has to be subtracted from the total number of ways. So 2 to the power 18 minus 1 is the answer for this question. Fine. Now you can also do it alternately like this. So since there were 18 different books and we have to select at least one book. So we can select either one book or 2 books or 3 books and so on till all 18 books. So 18C1 plus 18C2 plus 18C3 and so on, add till 18C18. And we already know the formula for NC0 plus NC1 plus NC2 till NCN, that is 2 to the power n. So we are adding from 18C1 till 18C18. So in 2 to the power 18 we have to subtract one term, which is 18C0. 18C0 is basically we are not selecting any book. Okay. 18C0 we know will be 1, NC0 is always 1. So it will be 2 to the power 18 minus 1. This is another way of looking at the same problem. Fine. Okay. Now let us look at the second part. The second part says we have to select at least one book on each subject. Okay. So what we do here is number of ways of selecting at least one reasoning book. So there are total 7 reasoning books. So for every reasoning book we have 2 choices. We will select or not select. So for 7 reasoning books we have 2 choices into 2 choices into 2 choices multiplied 7 times, which is 2 to the power 7. But that also includes one way in which none of the reasoning books are selected. So therefore this 1 has to be subtracted here. So basically it is 2 to the power number of books minus one way in which this one way is for the way where we are not selecting any reasoning book. So similarly, number of ways of selecting one quant book, at least one quant book, will be 2 to the power 6. 6 is the number of quant books minus 1. And similarly, number of ways of selecting at least one English book will be 2 to the power 5 minus 1, where 5 is the number of English books. So what is the number of ways of selecting at least one reasoning book and at least one quant book and at least one English book? That is how we will be selecting at least one book on each subject. So number of ways of selecting at least one book of each subject means we have to select at least one reasoning book, and we have to select at least one quant book, and we have to select at least one English book. So multiplication rule will be applied here. So multiply all the 3 ways and we will get the answer. Okay. This is the answer for the question. Fine. I hope it is clear. Now let us look at the next example where we have identical copies, right? Now this question gives you a little bit more specification that there are 7 identical copies of a reasoning book So all these 7 reasoning books are identical. 6 identical copies of a quant book. So all these 6 quant books are identical. And 5 identical copies of an English book. So now all the reasoning books are identical, all the quant books are identical, and all the English books are identical. Now how many ways can a person select at least one book? So we have the same 2 questions as in the previous slide, but here the books are identical. So let us look at first of all reasoning books. There are 7 identical reasoning books. Okay. Now let us look at the number of ways of selecting reasoning books. So if I am not selecting any reasoning book, means selecting 0 reasoning books, there is only one way. Not selecting any reasoning book, there is only one way. If I have to select one reasoning book, then there is only one way. Here you will notice the difference. Had all the 7 books been different, then selecting one book out of 7 different books, number of ways would have been 7C1, which is 7 ways. Because selecting one book is different from selecting the other book. But in this case, all the 7 books are identical. So it does not make any difference which book you have selected. So there is only one way of selecting one book here because all the books are identical. Fine. Now if you have to select 2 reasoning books, had all the reasoning books been different, then the number of ways would have been 7C2. Okay. But since here all the reasoning books are identical, so you can pick any 2 reasoning books, it will not make any difference. Okay. So there is only one way. You can pick any two reasoning books. There is only one way of picking 2 reasoning books because the books are identical. And similarly, for selecting 3 reasoning books, you have one way. For selecting 4 reasoning books, you have again one way. For selecting 5 reasoning books, you have only one way. For selecting 6 reasoning books, you have only one way. And for selecting 7 reasoning books, you have only one way. Beyond 7 we cannot go because there are in total only 7 identical reasoning books. Okay. So for 0 books, one way, 1 book, one way, 2 books, one way, and so on. 7 books also one way. So this one way is being added 8 times, right? Because from 0 to 7, these are 8 countings. 0 to 7, these are 8 countings. So this 1, 1, 1, 1, 1, 1, this will be counted 8 times. So what is the number of ways? Number of ways of selecting none or more of reasoning books is 7 plus 1, which is 8. So I am consciously using this 7 plus 1. This 7 is basically the number of identical reasoning books. You just have to add 1 to it. So total number of ways will be number of books plus 1, which is 8 ways. Okay. Because not selecting any book is also being included here, right? Similarly, number of ways of selecting none or more of quant books. It will be number of quant books plus 1. So 6 plus 1, 7 ways. Number of ways of selecting none or more of English books. That will be again number of English books plus 1. So 5 plus 1, which is 6 ways. So number of ways of selecting at least one book out of 18 books will be 8 into 7 into 6. Okay. So 8 into 7 into 6, when we do this, this also includes one way where we have not selected any reasoning book, where we have not selected any quant book, where we have not selected any English book. In short, we have not selected any book. But what does the question say? The question say that we have to select at least one book, right? So if we are not selecting any of the books, then there is only one way. So this one way has to be subtracted because we have to select at least one book. So total number of ways of selecting 0 or more books will be 8 into 7 into 6. But we have to select at least one book. So we have to subtract 8 into 7 into 6 minus 1. This 1 is number of ways where we are not selecting any of the books. So there are 335 ways. Fine. I hope the distinction is clear. When the books are identical, what do we have to do as compared to when the books were different? Fine. Okay. Now, second part of this question is we have to select at least one book on each subject. So, same question as in the previous slide, but now the books are identical. So, here we have to select at least one book on each subject, which means we have to select at least reasoning book, at least one reasoning book, and we have to select at least one quant book, and we have to select at least one English book. So, number of ways of selecting at least one book on each subject. So, in this case, we have to select at least one book. It means selecting zero book, or you can say selecting zero reasoning book is not to be counted, because we have to select at least one reasoning book. So, there are 7 ways, right? There are 7 ways. So, this is basically nothing but same as the number of reasoning books, right? So, if there are 7 identical copies of reasoning books, then selecting at least one reasoning book, the number of ways is same as the total number of reasoning books. It will be the same, these 7 ways, right? So, similarly, number of ways of selecting at least one quant book will be equal to the number of quant books, which is 6, and number of ways of selecting at least one English book will be equal to the number of English books, which is 5. So, that is 7 into 6 into 5. So, 7 is for selecting at least one reasoning book, and 6 is for selecting at least one quant book, and 5 is for selecting at least one English book. So, it's a case of and. We have to do all the 3 operations. So, multiplication rule will be applied, 7 into 6 into 5, which gives you 210 ways. Fine. I hope this point is clear. Alright. Now, let us look at this question. This question number 15 from sheet number 2127. It says in a party there are 15 guests and each of them shakes hand with every other guest once. Find the total number of handshakes that were exchanged at the party. Now, this question is a bit different because in this question you don't clearly know what we have to do, whether this is arrangement, whether this is selection, or what is the way of counting this. So we don't know anything about it, right? So let's do the plain counting. Let's go about this question in this way. Every guest shakes hand with the remaining 14 guests. So there are 15 guests, right? So suppose we are talking about 3 guests A, B, C. So if you take the guest A, then A is shaking hands with the remaining 14 guests, right? Similarly, B will also shake hand with the remaining 14 guests. Similarly, C will also shake hands with the remaining 14 guests, right? So, total number of handshakes will look like 15 into 14 because every guest is shaking hands with 14 other guests and there are 15 such guests. So, this 14 will be added 15 times, which is nothing but 15 into 14, which is 210. But there is a problem with this counting, right? What is the problem? The problem is that every handshake has been counted twice in this calculation. This calculation 210 has counted every handshake twice. So, for example, A shook hands with the remaining 14 guests. It means A shook hands with B, right? Because B is also one of the remaining 14 guests. Now, when you come to the counting for B, B also shook hands with remaining 14 guests. In these remaining 14 guests, A is also there. But when A shook hands with B, that time itself B also shook hands with A. जब A ने B से हाथ मिलाया, उसी टाइम B ने भी A से हाथ मिला लिया ना. तो B का जब हम काउंटिंग दोबारा से 14 बार कर रहे हैं, तो उसमें A वाली काउंटिंग एक बार फिर से हो जा रही है. So every handshake is being counted twice in this 210. So what will be the actual number of handshakes? Actual number of handshakes will be half of it because every handshake has been counted twice. So to correct that, we'll have to divide this 210 by 2. So it will be 15 into 14, which is 210, divided by 2, which is 105. Correct answer is 105. Fine. Now there is another way of looking at it. We can simply use the application of selection here. So alternatively, we can say that between every 2 guests in the party, there will be one handshake, right? You select any 2 guests in the party, between them, there will be exactly one handshake because the guests are shaking hands only once. Fine. So what we need to do is just select 2 guests out of 15 guests. So in how many ways can we do that? Selecting 2 guests out of 15 guests, 15C2, as simple as that. So 15C2 is the number of selection of every 2 guests in the party, and every 2 guests will have 1 handshake between them. So number of selections will be 15C2. For every selection there is 1 handshake. So just multiply 15C2 with 1, which is nothing but 15C2 only, right? So corresponding to each of the above 15C2 ways of selection, there will be 1 handshake. And hence their number of handshakes will be 15C2, which is after calculation 15 into 14 divided by 2, which is 105. Okay, you get the same answer. So basically it is just select 2 persons out of 15 persons. As many selections, those many handshakes, because every 2 guests are shaking hands exactly once, right? I hope it is clear. So answer is as simple as saying 15C2. Fine, I hope it is clear. Now let's look at the next example. It is related to this one only. Question number 16. So there are 20 friends who on the New Year's Eve exchanged greeting cards among themselves. So how many cards did they exchange all together? Fine. So every friend gives 1 greeting card to the remaining 19 friends. So total number of cards exchanged will be 20 into 19. Every friend is giving 1 greeting card to the remaining 19 friends. So total number of friends is 20 into 19. Because this 19 greeting cards will be added for all the 20 friends. So 19 added 20 times is same as saying 20 into 19. And here there is no problem of double counting, because as in the previous example, when A shook hands with B, that time itself B also shook hands with A. So there is only 1 handshake which is to be counted. But in this case, A gives a greeting card to B and B gives a greeting card to A. That means between these 2 people, 2 greeting cards are being shared. So here there is no problem of double counting. Okay. So answer is this 380 only. Fine. Or you can say it like this, that between every 2 friends there will be 2 cards exchanged, right? So you select 2 friends out of 20 friends. So 2 out of 20 friends can be selected in 20C2 ways, and for each of these selections there will be 2 cards exchanged. Okay. So corresponding to each of these 20C2 ways of selection, there will be 2 cards exchanged, and therefore total number of cards exchanged will be 2 into 20C2. So it will be 2 into 20C2 is 20 into 19 divided by 2. So this 2 and this 2 will cancel out. So we will still get 20 into 19, which is nothing but 380. Fine. And can you notice one thing? That 2 into 20C2 is nothing but 20P2, right? Because 2 can be written as 2 factorial. So NC2 or NCR into R factorial is nothing but NPR, right? We have studied this. So this can also be written as 20P2. And when you calculate 20P2, it is basically just multiply 20 with the next decreasing number 19. 20 into 19, that is 20P2, right? Fine. So answer is 380. Okay, let's look at this example. Question number 17. On a rail route between 2 stations A and B, there are exactly 10 stations. So between A and B, there are 10 stations. So if you include A and B, then there are total 12 stations. How many different tickets of a particular class are to be printed so that passengers can travel from any station to any other station? Okay, fine. So consider any 2 stations X and Y here. Okay. So a passenger can travel from X to Y as well as from Y to X, right? So if there are 2 stations X and Y, then traveling can be done from X to Y, or traveling can also be done from Y to X, right? So for these 2 travels, 2 different tickets are needed. So for example, if you travel from Delhi to Mumbai, you will need different ticket, and if you travel from Mumbai to Delhi, you will need a different ticket, right? So hence 2 tickets are required to be printed to travel between any 2 stations X and Y. Fine. Now including A and B, there are 12 stations. So in total there are 12 stations, out of which you can select any 2 stations. In how many ways? 12C2 ways, right? So there are total 12 stations. You can select any 2 stations out of 12. So number of selection is 12C2, because a person can travel between any 2 stations out of these 12 stations, right? So you can select any 2 stations in 12C2 ways, and corresponding to each of these 12C2 ways, which means corresponding to every selection of 2 stations, you will need 2 tickets to be printed, because a person can travel from one station to the second one, or he can travel from the second station to the first one, right? So for to and fro, you will need 2 different tickets. One ticket for to and one ticket for fro. So there should be 2 tickets printed for every 12C2 selection of 2 stations. So total number of tickets to be printed will be 2 into 12C2, which is again 2 into 12C2 is 12 into 11 by 2. So this 2 and this 2 will cancel out. So we'll get 12 into 11, which is 132. And similar to previous example, you can also write this as 12P2. Okay. Fine. So I hope this is clear. Now, next part of the discussion is finding number of routes from one place to other place. Okay. Such type of questions have appeared in the exam, and just take an example of this question. Okay, this is just an example. This figure gives you a grid of roads connecting city P and city Q. So here we have city P and here we have city Q, and what you see is a grid of roads connecting city P and Q. So question says, in how many ways can a person travel from P to Q, given that he can only travel southwards or eastwards on the grid lines? So southwards or eastwards means, so in the standard direction, this is north, this is south, this is east, and this is west. So from P to Q, a person can only come towards this direction, this is towards south, so he can only come downwards, or he can only go in this direction, this is east. Okay, fine. So these are the only 2 directions allowed here. So he can only move down or towards this direction. So how many ways of travel are there along the grid lines if somebody has to reach from point P to point Q? Okay. So in this case, whichever way a person chooses to travel from P to Q, he must have to take 5 steps eastwards and 3 steps southwards. Why? Because from P to Q, if you see, there are 5 steps eastwards. So we are counting this entire line as 1 step. Okay. So 1, 2, 3, 4, 5. Look at the pointer. 1, 2, 3, 4, 5. These are 5 steps eastward, and 1, 2, 3. 3 steps southwards. So whichever way he chooses to travel from P to Q, in every possible way, there will always be 5 eastward steps and 3 southward steps. So I'll just show you in this figure itself one way. Okay. So this is one way. So look at this yellow line. So some part of this yellow line is not visible. So let me I'll just erase it so that you can see it clearly. Okay. Fine. Now can you see that clearly? Okay. So focus on this yellow line. So far, whatever visible on this grid line, he has taken 1 step east, 1 step south, another step east. Further he takes 2 steps south, then he takes 3 steps east and he reaches Q. Okay, I'm just going to write it here. Let us denote the southward steps as S and eastward steps as E. Okay, so this particular yellow lines on the grid that you see, that can be written as, so route depicted in the figure can be written as ESE, SSEEE. So now look at my pointer on the grid. So east, then south. So this is E, S, E, S, S, E, E, E. That is what I have written here. Okay, fine. I hope you understood this. Now this is just one way. Alright. So we have to find total number of ways from P to Q. Okay. So number of ways a person can travel from P to Q is now nothing but arrangement of these letters only. Right. It is nothing different from all possible ways from P to Q. So this is one particular arrangement of all these letters. So how many E's are there? 5 E's, because there are 5 eastward steps. And how many S are there? 3 S, because there are 3 southward steps. So now for reaching from P to Q, this is one particular arrangement of E's and S's. So one particular arrangement gives you one way of reaching from P to Q. So the total number of ways in which you can arrange all these 8 things in a row will give you the total number of ways to reach from P to Q. Fine. So it is basically number of arrangements of these 5 E's and these 3 S in a row. So how many ways can we do that? 8 factorial by 5 factorial into 3 factorial. Where did that come from? Total we have 8 things to arrange. So 8 factorial. But all these 5 E's are identical. So divide by 5 factorial. So all these 5 E's are identical and of one type. So remember that formula, n factorial by p factorial into q factorial into r factorial, right? So this is the application of that formula. These 3 S are identical and of a second type. So total number of things are 8 factorial, divided by 5 E's are identical and 3 S are identical. So it is 8 factorial by 5 factorial into 3 factorial. Incidentally, that is also same as saying 8C5. Okay. So 8C5, or you can also write this as 8C3. It means the same. NCR is always equal to NCN minus R. So it will give you the same result. Okay. I hope this is clear. Fine. So now we'll do one thing. Let's take an example from your sheet and see how to solve that. It will be a similar one. This is a question from your sheet. This is sheet number 2128. This figure gives you a 9 cross 9 grid. Okay. In the previous example, we had 5 cross 3 grid. This is a symmetrical grid, 9 cross 9 grid. So we are doing the third part of this question, question number 9, third part. The other 2 parts we'll see how to deal with them later. Okay. In this case, we have to find the number of ways in which an ant can travel from A to B. It can travel only horizontally to the right or vertically up along the grid lines. So the ant has to move from A to B, and the ant can only move in this direction towards right, horizontally to the right, or vertically up. Okay. So whichever way the ant chooses to travel from A to B, it must have to take 9 horizontal steps and 9 vertical steps. Fine. Because it is a 9 cross 9 grid. So whichever way the ant chooses, she will have to travel 9 horizontally right steps and 9 vertically up steps. Fine. So I am just showing you one of the ways in the figure. So just focus on the yellow lines now. So this is one way of movement. This is how she can move. Right. Now let us denote the horizontal steps as H and vertical steps as V. So the route that I have just shown you in the figure, it can be depicted like this. So H, now focus on my pointer, right? H, V, H, V, 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 H, 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 V, H, H, V, 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 H, H. That is exactly what is written here. Fine. So what are we basically doing? This is one particular arrangement of 9H and 9V in a row. Fine. So one arrangement will give you one way of reaching from A to B. So the number of arrangements that you can do of these 9H and the 9Vs, each arrangement will be one way of reaching from A to B. So the number of arrangements will also be equal to the number of ways of reaching A to B. So what is the number of arrangements here? The number of ways an ant can travel from A to B is nothing but number of arrangements of 9H and 9Vs in a row, and that can be done in 18 factorial by 9 factorial into 9 factorial. So total 18 things are there, 9 plus 9. So 18 factorial divided by this 9H are identical, so divide by 9 factorial. These 9Vs are also identical, so divide by 9 factorial also. Once again, this is 18 factorial by 9 factorial into 9 factorial. Fine. So I hope this is clear. This is somewhat similar to the previous example. Or you can also write this as 18C9. I hope it is clear. Okay. Now let's look at this question. This is question number 5 on your sheet 2128, additional question. Okay. Now in this figure we have ABCD is a 6x6 grid, 6x6 square grid, as you can see in the figure. So we are right now doing just the third part of this question. The other two parts we'll see how to deal with those two parts. Right now we are looking at only the third part of this question. So third part says, in how many ways can an ant go from P to R without going through Q? And it can go only horizontally to the right or vertically up. So again we will use H for horizontal and V for vertical. Fine. Okay. Now since we have done the previous examples, in this example we will not see one of the ways. We will just apply the learnings from the previous two examples, and we can apply here and see what is being done. So all possible number of ways from P to R. How many ways? So just focus on P to R, okay? So from P to R, 1, 2, focus on the pointer. 1, 2, 3, 4, 5. 5 horizontal, 1, 2, 3, 4, 5. 5 vertical. So from P to R, we have 5 horizontal and 5 vertical ways. So basically, 5 horizontal and 5 vertical steps, not ways. 5 horizontal and 5 vertical steps. So there are total 10 steps. So it will be 10 factorial divided by 5 factorial into 5 factorial. This 5 is for 5 horizontal, which are all identical, and these are for 5 vertical, which are all identical. And this can also be written as 10C5. So as we have seen in the previous example, you can also use the formula for combination. This is basically 10C5. Okay. This gives you all possible routes from P to R. What is the number of ways from P to Q? From P to Q it is 1, 2, 3 horizontal, 1, 2, 3 vertical. Okay. So total number is 6, and you can select 3 out of those 6 steps. So 6C3, or you can say 6 factorial by 3 factorial into 3 factorial, because all 3 horizontal steps are identical, all 3 vertical steps are identical. So number of ways from P to Q is 6C3. Similarly, number of ways from Q to R will be 4C2. Let's look at Q to R. 1, 2 horizontal steps 2, 1, 2 vertical steps 2. So total 4, and out of 4 you select any 2. So 4C2, or you can say 4 factorial by 2 factorial into 2 factorial. So number of ways from P to Q, number of ways from Q to R. So what will be the number of ways from P to R via Q? So we are going from P to R via Q. So number of ways from here to here and number of ways from here to here will be multiplied, Remember the first few things we discussed in this chapter, permutation and combination, multiplication principle of counting, right? So number of ways of going from A to C via B is nothing but A to B number of ways into B to C number of ways. Because the person has to go from A to B also and B to C also. So number of ways of going from P to R via Q is nothing but number of ways of going from P to Q and from Q to R. So from P to Q these many ways, from Q to R these many ways. We have already calculated here in the above steps. So number of ways from P to R via Q is 6C3 into 4C2. Okay. So number of ways of P to R without going through Q. So this is number of ways from P to R via Q. But if we have to go from P to R without going through via Q, then it will be total number of ways 10C5 we had calculated initially. So total number of ways of reaching from P to R is 10C5, out of which these many ways are going through Q or via Q. So if we do not want to go via Q, then how many ways? 10C5 minus 6C3 into 4C2. Okay. So now the rest is just calculation. So we will do the calculation here and we will get the answer is 132. Okay. So the answer is 132. I hope it is clear. So this is a wonderful combination of, you can say, question on concept of finding the roots and the application of the first basic things, the first basic thing that we learn in permutation and combination, the fundamental rule of counting, the multiplication rule. Fine. I hope it is clear. Alright. Now let us look at a concept known as derangement. What is derangement? So suppose there are n letters and n corresponding addressed envelopes. Okay. So there are addresses written on envelopes. The number of ways of placing these letters into the envelopes such that no letter is placed in its corresponding envelope is referred to as derangement. So there are n letters and n corresponding addressed envelopes. So for example, let's take some number, 5 letters and 5 corresponding addressed envelopes. It means every letter, and these are all different. By default, these are all different. So 5 different letters and 5 different addressed envelopes. So there are different addresses written on the envelopes. Now every letter has a corresponding envelope in which it is supposed to go so that it reaches the correct address. Fine. So every letter has a corresponding correct envelope to be put into. But what is derangement here? The number of ways of placing these letters into the envelope such that no letter is placed in its corresponding envelope is referred to as derangement. So none of the letters should get into the correct corresponding envelope. The number of ways of doing this is known as derangement. Okay. Or you can simply say the number of ways of putting every letter into the wrong envelope. I am stressing the word every. The number of ways of putting each and every letter into a wrong envelope, that is known as derangement. The number of ways, that is known as derangement. Now the number of derangements of n objects is given by, so suppose we have n letters and n corresponding addressed envelopes. If we have to find the number of ways in which no letter gets into the correct envelope, or you can say, in other words, every letter, each and every letter gets into an incorrect envelope, that number of ways is given by this formula. Okay. So it is given by dn. dn, this small n is for the number of objects. So if there are 5 objects, then we'll write it as d5. If there are 3 objects, we'll write it as d3. So dn is given by n factorial multiplied with 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial plus and so on till last term will be minus 1 whole to the power n into 1 by n factorial. Fine. You can also write this formula as n factorial into, you can start from 1 by 2 factorial. There is no harm. 1 by 2 factorial minus 1 by 3 factorial plus 1 by 4 factorial and so on. Okay. The next term here will be minus and so on. Because this is 1 and 1 by 1 factorial is again 1. So this 1 minus 1 is anyways going to be 0. So these two terms, the first two terms will not contribute anything to this entire calculation. So you can start from 1 by 2 factorial also. Right? Okay. So this is the formula for derangement of n objects. Fine. Okay. Now it will help if you remember some values for dn, so that if there is a question you will be able to save some time. So if you remember, well and good. So d1 is 0. So number of ways of putting only one thing into incorrect place is 0. d2, number of ways of putting two objects into incorrect envelopes, two letters into incorrect envelopes, there is only one way. d3 is 2. So number of ways of putting three objects into incorrect places is 2. d4 is 9. d5 is 44. d6 is 265 and so on. Obviously we can't remember all the values for dn. So if you can remember these 6, it will be well and good. It can save you some time. Fine. Okay. Now let us look at a question on this. So this is a question in sheet number 2128 and it is question number 10. This question says there are 8 letters and 8 corresponding envelopes. Okay. Each envelope can hold only one letter. Fine. So first question is, in how many ways can the letters be placed into the envelopes? So it is not asking about correct or incorrect. It is just saying there are 8 letters and 8 corresponding envelopes, but it is not asking you to put the letters into corresponding envelopes. This first part is only asking you in how many ways can the letters be placed into the envelopes, and you can place only one letter into one envelope. So total number of ways that these letters can be placed into envelopes is 8 factorial. How? Because these are 1, 2, 3, 4, 5, 6, 7, 8 places. So let's consider these are all envelopes. So here you have 8 choices for the letters. You can put any one of the 8. Then here you will have 7 choices, because now only 7 are left. Then here you will have 6 choices and so on. So it will be 8, 7, 6, 5, 4, 3, 2, 1, all of them multiplied together, which is nothing but 8 factorial. Okay. So this is all possible ways of placing all the letters into the envelopes. Neither correct nor incorrect. This is just about placing all the letters into the envelopes. Second part is saying in how many ways can each letter be placed into its corresponding envelope. So here corresponding means you have that each letter has to be put into the correct envelope. Okay. So how many ways are there? There is only one way. Okay. If each letter has to get into the correct envelope, then you have only one choice. You have to put the letters into the correct envelope. You can't shuffle it in any other way. There is only one way of putting each letter into correct envelope. So putting n objects into n correct places which are designed for them, which are designated for them, that there is only one way. There is only one way of doing the correct thing. So in how many ways, third part, in how many ways can exactly one letter be placed into a wrong envelope? So here you have to place exactly one letter into a wrong envelope. Okay. So as we will see, this is not possible. Why not possible? Let's consider an example. So if one letter, let us say L1, is placed into a wrong envelope, say E2. Suppose L1 was supposed to get into E1, the correct envelope, but instead you are placing L1 into incorrect envelope, which is E2. Fine. Then the letter L2 if you are placing the letter L1 in the wrong envelope E2, it means the letter L2 is not going into the correct envelope E2. It will be going to some other envelope. So it will automatically, L2 will automatically go into an incorrect envelope. So L1 already went into an incorrect envelope, and correspondingly L2 now will also get into an incorrect envelope because L2 cannot get into E2 now. E2 has already been occupied. So it means L2 is also placed into another wrong envelope. We can say, let's say E5. It can be any E3, E5, E7, it can be anything. But L2 will definitely not go into E2 because E2 has already been occupied by L1. So in this case, L1 also went into incorrect envelope and L2 is also getting into incorrect envelope. So there is no way you can place only one letter into incorrect envelope. Okay. There has to be at least two letters which will go into incorrect envelope. A single letter cannot get into an incorrect envelope. Fine. So what is the required number of ways? 0. There is no way. Okay. What about this? In how many ways can exactly 7 letters be placed into their corresponding envelopes? In how many ways can exactly 7 letters be placed into their corresponding envelopes? This is just another version. This question is just another version of the above question. How? If you are placing exactly one letter into an incorrect envelope, it by default means, or it automatically means, that you are placing the remaining 7 letters into the correct envelope. But this is not possible, right? So naturally this is also not possible. Fine? Or you can simply say it like this, that if 7 letters are placed into the corresponding correct envelopes, then the 8th letter will definitely or automatically get into the correct envelope only, right? If 7 letters are getting into correct envelope, then the 8th one has to get into the correct envelope. So you can't place only 7 into the correct one. Fine. So again, required number of ways is 0. Fine. There is no way. Okay. Now let us look at, till now we did not need the formula for derangement. Now we will need that. So fifth part of this question says, in how many ways can exactly 3 letters be placed into wrong envelopes? So now here comes the question on derangement. You have to place exactly 3 letters into wrong envelopes. Now see, if the question had been, you have to place all the 8 letters into wrong envelopes. Okay. In that case, it was as easy as saying, apply the formula for D8. Apply the formula for D8. But here the question is a bit tricky. It says, in how many ways can you place exactly 3 letters into wrong envelopes? So how many letters are there? In this question there are 8 letters, out of which you have to place exactly 3 means only 3. Neither more nor less. Exactly 3 means 3, no more, no less. So exactly 3 be placed into wrong envelopes. So first of all, what you will have to do is, you will have to select those 3 letters, because all the letters are different, right? So those 3 letters which are getting into incorrect envelopes can be any 3 letters. So there are several possibilities. So first you will have to select 3 letters. So 3 letters are placed into wrong envelopes means 5 letters are placed into corresponding envelopes. Okay. So you can think it in a different perspective. Since you are saying 3 letters are placed into wrong envelopes, it by default means that the remaining 5 are getting into correct envelopes. Why? Because it says exactly 3. So if exactly 3 or only 3 letters are placed into wrong envelopes, it means the remaining 5 are being placed into correct envelope, right? So first you have to select those 3 letters which will get into the incorrect envelope, or you can also do it other way around. First you have to select 5 letters which will get into the correct envelope. So the remaining 3 will automatically get into the wrong envelopes. Okay. So you can do it 2 ways. First select those 3 letters which will get into the wrong envelopes, or you first select 5 letters which will get into the correct envelopes. Either way you will get 8C3 or you will get 8C5. But either way you will get the same number. Why? Because 8C3 is equal to 8C5, isn't it? NCR is always equal to NCN minus R. So 8C3 will be equal to 8C5. Fine. So in this case, we can do it this way. Select those 5 letters which will get into the correct envelopes, so that remaining 3 will get into the wrong envelopes. Okay. So the correct ones can be selected in 8C5 ways. Now this is just selection. Okay. Now these 5 letters which are getting into correct envelopes can be put into the correct envelopes in only one way. So actually it is 8C5 into 1 also, because this 8C5 is only for selection. Once you select, in how many ways can you put those 5 letters into the correct envelopes? It is 8C5 into 1. And now the remaining 3, now the 3 are automatically left, which are remaining 3. Those remaining 3, all of them can be placed into wrong envelopes in D3 ways. Now 8C5 is 56 and D3, as we have seen in the previous slide, the value is 2. So the answer is 112. Fine. Let's look at the sixth part. In how many ways can exactly 4 letters be placed into their corresponding envelopes? So we have to place 4 letters, exactly 4 letters into corresponding means correct envelopes. So 4 letters placed into correct envelopes, then remaining 4 letters will be placed into wrong envelopes. So if only 4 letters are getting into correct envelopes, it means the remaining 4 letters will get into the wrong envelopes. So the wrong envelopes, the letters going into wrong envelopes, they can go in D4 ways. These 4 letters, each one of them are going into wrong envelopes. That can be done in D4 ways. So out of the 8 letters, any 4 letters can be placed into corresponding envelopes in 8C4 ways. The 4 letters which you are placing in correct envelopes can be selected in 8C4 ways. So the remaining 4 automatically, the leftover will be remaining 4, they will get into incorrect envelopes. So now you select 4 letters which will get into the correct envelopes in 8C4 ways, and all of them can be placed into correct envelope in only one way. The remaining 4 letters will get into incorrect envelopes in D4 ways. So 8C4 is 70 and D4, as we have seen in the previous slide, it is 9. So 70 into 9 is 630. Okay. So here the answer is 630. I hope you have understood the concept of derangement. Now this will be all in this part of the session. In the second part of this session, we'll look at few more concepts related to permutation and combination. Okay. Thank you. Hello students. Welcome to Time Classes. This session is part 2 of the third session on permutation and combination. And in this session, we are going to learn about how to do circular arrangements, and we will start with the concept of distribution. I hope you have the handout QAHO 2127 and 2128. So let's begin with the session. So what is circular arrangement? So we have already learned that when n distinct things are arranged linearly, means in a row or in a line or in a queue, then we will get n factorial ways, right? If n distinct things are arranged in a line, or we have a linear arrangement of n distinct things, then we will get n factorial ways. But if we have to arrange n distinct things around a circle, in that case we will get n minus 1 factorial ways. Okay. So in that case, number of arrangements will be n minus 1 factorial. Fine. Why is that so? Let us understand with an example. Suppose we have 3 persons A, B, C. Okay. If they were to be arranged in a row, then how many arrangements do we have? If they were to be arranged in a row, means linear arrangement, then we would have 3 factorial ways, right? Because these are 3 distinct things to be arranged in a row. So that means 6 ways, right? 3 factorial means 6 ways. So if I have to do those 6 arrangements in a circle, then these are those 6 arrangements. Okay. These 3 factorial arrangements, which would have been the case when we will do linear arrangement, those same 3 factorial, which is 6 arrangements, has been done here in case of circle. Now look at these 3 arrangements in the top row and these 3 arrangements in the bottom row. Okay. So if you look at this arrangement from here, if you look at the first arrangement, let us say this is the first arrangement. If you look at this arrangement from this place, if you look the second arrangement from this place, and if you look at the third arrangement from this place, then you will find all these 3 arrangements as exactly the same, because in the first arrangement you will see that right in front of U there is A, to the left of A there is B, and to the right of A there is C. If you look at the second arrangement from this place, then you will see that A is right in front of U, B is to the left of A, and C is to the right of A. If you see the third arrangement from this place, then A will be right in front of U, B will be to the left of A, and C will be to the right of A. So we can say that these 3 arrangements are not really different. They are the same, because a circle does not have an end point, right? So these 3 arrangements are considered to be the same. Or you can also think of these 3 arrangements in a way like, if you rotate this arrangement by 120 degree clockwise, you will get this arrangement, and if you rotate this arrangement by further 120 degree clockwise, you will get this arrangement. So we can say these 2 arrangements can be obtained from the first arrangement just by rotation. Fine. So we'll consider all these 3 arrangements as same, not different. But this arrangement, the first arrangement in the bottom row, this is different from the arrangements in the top row, because in this case C is to the left of A and B is to the right of A, whereas in the previous case C was to the right of A and B was to the left of A. In this case it is just opposite. Okay, C is to the left of A and B is to the right of A. So this arrangement is certainly different from the above arrangement. Fine. But again, these 3 arrangements are the same, because this arrangement can be obtained from this just by rotation of 120 degree clockwise, and if you rotate this further by 120 degree clockwise, you will get this arrangement. So these 3 arrangements are all same, and these 3 arrangements are all same, but these 2 arrangements are different. So how many different arrangements do we have? Only 2 here. Okay, fine. So if we have to arrange these 3 persons in a row, it won't be 3 factorial, it will be actually 3 minus 1 factorial, and which is equal to 2 factorial, which is equal to 2 ways. So there will be only 2 ways. So arrangements in the top row are all the same, and arrangements in the bottom row are all the same. So actually we have only 2 different arrangements. What happens here is this: unlike linear arrangement, circular arrangement does not have an end point. In case of a linear arrangement, you will have an end point, right? But in case of circular arrangement, there is no end point. Hence, first we need to fix one item out of n distinct items. Okay. So to have an end point, you have to fix one item first, and then you can arrange the remaining n minus 1 items in n minus 1 factorial ways. Okay. That is why in case of circular arrangement of n distinct things, number of arrangements will be n minus 1 factorial. Fine. Now in the above example, the clockwise and anti-clockwise arrangements of 3 persons are different. Okay. So what do we mean by this? Let's take these two figures. So I am taking this figure and this figure here. So we said these are two different arrangements, right? These two are different arrangements, because in this case, if you look at the clockwise arrangement, it is ABC. Okay. And in this case, if you look at the clockwise arrangement, then it is ACB. So in this case, it is ABC clockwise. In this case, it is ACB clockwise. So here the clockwise and the anti-clockwise arrangements are different. Okay. Fine. So these will be counted as two different arrangements. Now let us look at this example. Let us consider arrangements of 3 different colored beads or flowers. Now we are talking about different colored beads or flowers, and let's name those beads or flowers as x1, x2 and x3. Let's arrange them in a circle to form a garland. Okay. In that case, if we compare it with the two arrangements in the previous case, x1, x3 and x2 clockwise, and in this case x1, x2 and x3 clockwise. So here if you look at clockwise, we have x1, x3, x2. Here we have x1, x2, x3. Okay. So if these were persons, then we would count these two as different arrangements. But in this case, because we have beads or flowers, the clockwise arrangement and the anti-clockwise arrangements is considered as same in this case. And why is that so? The reason is this: because you can get one of the arrangements from the other just by flipping over. Now remember, in the last slide we said the arrangements in the first row were all the same because the other two arrangements could be obtained from the first arrangement just by rotation. Okay. Similarly, the 3 arrangements in the bottom row were same because in the bottom row the last 2 arrangements could be obtained from the first arrangement just by rotation. So the arrangement which can be obtained by just rotation of the previous arrangements, we consider them as same, right? In this case, these two arrangements are also the same because you can pick this garland by putting your hand beneath the garland and just pick it up and flip it over. Okay. Just pick the garland and flip it over. When you flip it over, you will get this arrangement. So in this case, we will say that this second arrangement can be obtained from the first arrangement just by flipping it over, and therefore we will consider both the arrangements as same. This is not possible in case of arrangements of people. You can't pick the table and the people from beneath and just flip them over. That will not be the same arrangement, right? Because whereas in this case, beads or flowers, you can consider them as nearly spherical objects. So if you pick the garland and flip it over, then you get the same arrangement. Okay. So in this case, what will happen is that number of circular arrangements will have to be divided by 2 because the clockwise and anti-clockwise arrangements will be the same. Fine. So in a nutshell, we will say the number of circular arrangements of n distinct items is n minus 1 factorial if clockwise and anti-clockwise arrangements are different. Fine. And it will be n minus 1 factorial divided by 2 if clockwise and anti-clockwise arrangements are the same. So normally in case of arrangements of people, the clockwise and anti-clockwise arrangements will be different. And in case of arrangements of beads or flowers around a circle to form a garland, in that case clockwise and anti-clockwise arrangements would be the same. So in case of questions on beads or flowers, you have to divide n minus 1 factorial by 2 to get the number of circular arrangements. Fine. Okay. Now let us look at this example. This is question number 19, first part, handout number 2127. In how many ways can 6 persons be seated around a circular table? So we are talking about 6 persons, and persons by default are all distinct. and we have to seat them around a circular table. So n persons can be arranged in a circular table in n minus 1 factorial ways. So here n is 6. So the answer is 6 minus 1 factorial, which is 5 factorial. Fine? Easy? In how many ways can 7 distinct flowers be arranged on a garland? Now in this case, this is a question on garland. So n flowers can be arranged in a garland in n minus 1 factorial by 2 factorial. This 2 factorial is nothing but 2. These many ways. Right? Because here anti-clockwise and clockwise arrangements will be counted as same. So how many flowers are there? 7. So we'll have 7 minus 1, which is 6 factorial divided by 2. The answer is 360. Fine. I hope these two problems are clear. This is a straightforward example of what we learned in the theory part of circular arrangement. Okay, now let's look at this question. The question says, in how many ways can 7 boys and 7 girls be seated around a circular table such that no 2 girls sit together? Okay. So it is the case of no 2 girls sitting together, right? So what do we do first? We have done such examples. So when no 2 girls sit together, since the restriction is on the girls, first we'll arrange all the 7 boys in a circle. Okay. So 7 boys can be arranged in 7 minus 1 factorial, which means 6 factorial ways in a circle. We have to arrange them in a circle. That is why n minus 1 factorial. So 7 boys can be seated in 6 factorial ways in a circle. Fine. Now once we do that, we are going to arrange the girls in the gaps between the boys, right? So how many gaps will be there? So there will be 7 such gaps, right? Now if you remember, if we arrange 7 boys in a row, then gaps will be 1 more than the number of boys. Gaps will be 7 plus 1, 8, right? You remember we have already discussed this while discussing linear arrangement. But since here in this case we are arranging the boys in a circle, so 1, 2, 3, 4, 5, 6, 7, these are 7 boys. Girls will be sitting between the boys. So how many gaps are there? I am representing the gaps by a cross. 1, 2, 3, 4, 5, 6 and 7. So there will be only 7 gaps. Okay. So these are 7 gaps available for the girls, and we have 7 girls also. So the 7 girls can be arranged in these 7 gaps in 7 factorial ways. Okay. The 7 girls can be arranged in these 7 gaps in 7 factorial ways. Here we do not have to do 7 minus 1 factorial, because since the boys were already arranged, we already have a reference point, right? What we discussed in the theory part of circular arrangement is this: since there is no end point in a circle, first we have to fix one thing and then n minus 1 things can be arranged. But in this case we have already placed the boys, so we already have a reference point. So 7 girls can be arranged in 7 gaps in 7 factorial ways. Fine. So what is the total number of ways? First you arrange the boys in 6 factorial ways and then you arrange the girls. So 6 factorial into 7 factorial. Fine. This is the number of ways. Now second part. In how many ways can 8 beads be arranged in a necklace such that the 3 particular beads are always together? So this is a case of things being kept together. So these 3 particular beads, let's treat them as a single unit. Okay. Let's treat them as a single unit. So we have 8 beads and 3 particular beads are to be always together. So 1, 2, 3, 4, 5, 6, 7, 8 and 3 beads, 3 particular beads. Suppose these 3 are those 3 particular beads. These 3 have to be together. So we'll club them together and count them as a single unit. So now how many things do we have? 1, 2, 3, 4, 5 and 6. So we have now 6 items to arrange in a circle because it is a case of necklace. Okay. So now these are 6 beads because these 3 beads are counted as 1. Now there are 6 beads and they can be arranged in a garland. We have to form a garland or a necklace. Okay. In this case it is a necklace. We can say that it is a garland. Okay. So in how many ways can we do that? 6 minus 1 factorial divide by 2. Why divide by 2? Because the case of a garland or a necklace. So 5 factorial by 2. Okay. These many ways. Now the 3 beads which were together, they also can be arranged amongst themselves in 3 factorial ways. Right. They will be together but they can arrange among themselves in 3 factorial ways. So total number of ways will be 5 factorial by 2 multiplied with 3 factorial. So when you do that, you will get 360 ways. Fine. I hope it is clear. Okay. Now let us look at this question. This is just an extra question. So there are 12 friends who went to a restaurant for a party. There were 2 round tables, one small table with 5 chairs and another bigger table with 7 chairs. So these are 2 round tables. Okay. In how many ways can the seating arrangement of these 12 friends be done at the 2 tables? Fine. Now since there are 2 tables and total number of chairs are also 12, 5 on the smaller table and 7 on the bigger table. But since there are 2 different tables, so in this case first we will have to select those 5 friends out of the 12 who are to be seated at the smaller table. So we will have to do the selection first before doing the arrangement. So first we have to select 5 friends which will sit at the smaller table because it can be any 5 of the 12 friends. Fine. So you can either select 5 friends out of 12 to be seated at the smaller table, or you can select 7 friends out of 12 friends to be seated at the bigger table. You have to do any one of these, not both, because once you select 5 friends, then the remaining 7 will automatically sit at the bigger table. Or once you select 7 friends for the bigger table, the remaining 5 will automatically sit at the smaller table. So you can do the selection of either 5 friends or 7 friends, any one of them. So suppose we select 5 friends out of 12 friends who are to be seated at the smaller table. So the remaining 7 friends will automatically sit at the bigger table, right? For them we don't have to do another selection. So 5 out of 12 friends can be selected in 12C 5 ways. Okay. And once we have done this selection, now we have segregated 5 people and 7 people to be seated at the respective 2 tables. Now once you do this selection, the next step is we have to arrange, because the question is about seating arrangement. So the 5 friends at the smaller table can be seated in 5 minus 1 factorial ways, which means 4 factorial, because it is a round table, right? And the remaining 7 friends at the bigger table can be seated in 7 minus 1 factorial ways, which is 6 factorial ways, because again it is a round table. Fine. So what is the total number of ways? First we selected, then we arranged 5 people, and then we arranged 7 people. Okay. So 12C5 into 4 factorial into 6 factorial. So these many ways will be there. Fine. I hope it is clear. Alright. Now let us look at this question. This is also an additional question. It is saying there is a square table with 2 chairs on each side. Now here we have to do the arrangement on a square table. This square table with 2 chairs on each side. So we have to find in how many ways can 8 persons be arranged around the table. So there are total 8 chairs, 2 chairs on each side. So the table and the chairs will look something like this. So it's a square table, so all its 4 sides will be identical, right? It's a square table, so all the 4 sides are equal, so all the 4 sides are identical. So we can choose any one side first of all. So we can start by fixing a person on a chair on any one side. So you can take any one side since all the sides are identical. So there is only one way of selecting a side, right? There are not 4 ways because all the 4 sides are identical. But on each side there are 2 chairs. So suppose I select this side, the bottom side. There are 2 chairs, 1, 2. So this is the left chair and this is the right chair. Fine. So we can start by fixing a person on a chair on any side. Now since there are 2 chairs on each side, this person can be seated in 2 ways. So these are 2 chairs. I have selected the bottom side and these are 2 chairs on this side. So this is the left chair and this is the right chair. Okay. So for fixing the first person, you have 2 choices. You can make him sit at this chair or you can make him sit at this chair. Fine. So this person which you have selected can be seated in 2 ways on any one of the sides. And then once you fix that person, the remaining 7 can be seated in 7 factorial ways. Now what will happen is once you fix this person, that can be done in 2 ways, you will be left with 7 chairs and 7 persons also. So you can arrange those 7 persons in those 7 chairs in 7 factorial ways. Okay. Now we are taking this up from the basics of circular arrangement only. There also we fix 1 person. Okay. And then we fix the remaining n-1 person. But here for fixing 1 person, because this is not a round table, it's a circular, it's a square table. So there are 2 chairs on each side. So whether you make the person sit on this chair or this chair, these are 2 different ways. So for the first person to be fixed on 1 chair, there are 2 ways, and then you can fix the remaining 7 persons in 7 factorial ways. Fine. I hope it is clear. Now let us look at distribution. So while doing questions on distribution, these are the 2 steps which will be followed. Step number 1 will be formation of parcels, and that will be followed by distribution of parcels. Okay. So first thing we'll clear in our mind is distribution is not permutation, distribution is not combination, distribution is something else. Distribution is formation of parcels followed by distribution of parcels, but of course we'll be using the concepts of permutation and combination here as well, but it is not exactly permutation or exactly combination. It is formation of parcels followed by distribution of parcels. Fine. So in questions we'll have to be careful about whether we have to just form the parcels or after forming the parcels we'll have to do the distribution also. We'll have to judge in the question whether only formation of parcels is required or formation of parcels is to be followed by distribution of parcels as well. Fine. So now let us look at some examples to understand all this. So let us distribute 10 different chocolates into 2 lots of 6 chocolates and 4 chocolates. So we have to distribute the chocolates into 2 lots of 6 chocolates and 4 chocolates. Although the word says distribute, but in this case you will understand that we just have to segregate 10 different chocolates into 2 groups, one of 6 chocolates and the other one of 4 chocolates. So it is basically formation of 2 parcels, one parcel having 6 chocolates and another parcel having 4 chocolates. So this question is only about formation of parcels. Okay. You just have to segregate these 10 different chocolates into 2 groups or 2 lots. So this is how we can do this. So out of 10 different chocolates, you select 6 chocolates first. So 10C6, and then the 4 remaining chocolates, they are themselves another lot. So once you selected 6 chocolates out of 10, the remaining 4 is by default another lot. Okay, so it is basically 10C6 into 1, or you can also understand it in this way. First select 6 chocolates out of 10, then you are left with 4 chocolates. Out of those 4 chocolates, you have to select all 4 of them to form the second parcel. 4C4 is nothing but 1. So that is why I said once you selected 6 chocolates, the remaining 4 chocolates, they automatically become another lot. Fine. Now, when you put the formula like this, 10 factorial by 6 factorial into 4 factorial, right? And this 4C4 is nothing but 1. So this is what you get. 10C6 is nothing but 10 factorial by 6 factorial into 4 factorial. Fine. Now suppose we have to distribute these 10 different chocolates among 2 kids such that one of them gets 6 chocolates and the other one gets 4 chocolates. Fine. So in that case, what do we have? Distribute 10 different chocolates among 2 kids such that one of them gets 6 chocolates and the other one gets 4 chocolates. In this case, first we have to form the parcels. So we have to form 2 parcels, one of 6 chocolates and the other one of 4 chocolates. And then we also have to distribute those 2 parcels among 2 kids, right? So this is distribution of parcels followed by formation of parcels. So in this case, 10C6, this 10C6 is for formation of parcels, and into 2 factorial, that is for distribution of parcels. So when you write the formula for 10C6, it will be 10 factorial by 6 factorial into 4 factorial, and this whole thing to be multiplied with 2 factorial, right? So this 10C6 is for formation of parcels, and it is to be followed by distribution of parcels in this case. So into 2 factorial also. So this 2 factorial is for distribution of parcels. Fine. I hope you understood the difference between this and this. So in the first part, we only had to form the parcels. In the second part, we had to distribute the parcels after the formation of parcels. Fine. Okay. Now suppose in this case, third case, suppose distribute 10 different chocolates into 2 lots of 5 chocolates each. Here the lots are equal. 5 chocolates in one lot and 5 chocolates in other lot, right? In that case, what will happen is, it will be 10 factorial by 5 factorial into 5 factorial by 2 factorial. So it came out like this: 10C5, you select 5 chocolates out of 10, the remaining 5 is automatically the second lot, and you have to divide this by 2 factorial. Why divide this by 2 factorial? Because these 2 lots of 5 chocolates each will be identical. Okay, these 2 lots of 5 chocolates each will be identical. So since we already formed the parcels and each of them have 5 chocolates, they will be considered as identical because they both have same number of chocolates. Fine. And remember, there is no name written on these parcels. These are not addressed parcels. These are just packets with no name written on them. Fine. So these 2 parcels will be identical, each having 5 chocolates. So that is why you divide by 2 factorial also. So when you expand this using the formula, you will get 10 factorial by 5 factorial into 5 factorial. This 2 factorial is for identical lots. Now distribute 10 different chocolates among 2 kids, each kid getting 5 chocolates. right? So in this case, you don't have to do anything. Just we have already formed the parcel. This is the parcel. In this, you multiply 2 factorial because there are 2 kids. So this is formation of parcel and followed by distribution of parcels. So in this case, we will have 10 factorial by 5 factorial into 5 factorial into 2 factorial, and this entire thing has to be multiplied by 2 factorial also. This is for distribution of parcel. Okay. So this entire thing, the terms inside the bracket, this is for formation of parcels, which we did in the previous case, and into 2 factorial, this is for distribution of parcels. So here you will get 10 factorial by 5 factorial into 5 factorial, because this 2 factorial will cancel out with this 2 factorial. Alright. So in a nutshell, we will say number of ways of dividing P plus Q items into 2 groups of P and Q items respectively. So here P is not equal to Q. Okay. So it is the case of 6 chocolates and 4 chocolates. So it will be P plus Q factorial by P factorial into Q factorial. So basically it is 6 plus 4, 10, 10 factorial by 6 factorial into 4 factorial, right? This is what we get. Number of ways of dividing 2 P items into 2 equal groups of P each. So for example, 10 chocolates to be divided into 5 chocolates and 5 chocolates, 2 lots. In that case, 2P factorial. So in this example, our P is 5. So 2P is 10, 10 factorial divided by 5 factorial into 5 factorial, which is nothing but 5 factorial square. So if 2P items have to be divided into 2 equal groups of P each, then 2P factorial divided by P factorial into P factorial, that becomes P factorial square. This is to be done when 2 groups have distinct identities. This is to be done when 2 groups have distinct identities. Fine. So for example, when you distributed the lots to 2 different kids, then the identities of the parcels became different. So in that case, it will be 10 factorial divided by 5 factorial into 5 factorial. But the number of ways of dividing 2P items into 2 equal groups of P each, where the 2 groups do not have distinct identities, in that case 2P factorial divided by P factorial into P factorial, and this 2 factorial also should be multiplied in the denominator, because the 2 lots or the 2 groups, equal groups, do not have distinct identities in this case. So which means they are identical. So if they are identical, you have to divide by 2 factorial. Fine. Okay. Now let us say distribute 10 different chocolates into 3 lots of 2 chocolates, 3 chocolates and 5 chocolates. Here we just have to form the parcels. So 10 factorial by 2 factorial into 3 factorial into 5 factorial. Fine. Now distribute 10 different chocolates among 3 kids such that one of them gets 2 chocolates, other one gets 3 chocolates and the third one gets 5 chocolates. So this is a question where formation of parcels is to be followed by distribution of parcels among 3 kids. So formation of parcels multiplied by 3 factorial. Why 3 factorial? Because there are 3 kids. So these parcels can be distributed among 3 kids in 3 factorial ways. Fine. So this is for formation of parcels and this is for distribution of parcels. Distribute 10 different chocolates into 5 lots of 2 chocolates each. So 10 factorial divided by 2 factorial, 2 factorial, 2 factorial, 2 factorial, 2 factorial, and this 5 factorial is because all these 5 lots having 2 chocolates each will be identical. Fine. Now distribute 10 different chocolates into 5 kids, each kid getting 2 chocolates. Now this is formation of parcels followed by distribution of parcels. So we already formed the parcels here. For distribution, since there are 5 kids, so you multiply by 5 factorial. Okay. So these 5 parcels, each parcel having 2 chocolates, can be distributed among 5 kids in 5 factorial ways. So here you multiply 5 factorial. So you'll be left with this quantity only. Okay. So this part is formation of parcels, and this 5 factorial which you multiplied, that was distribution which followed the formation of parcels. Fine. So number of ways in which P plus Q plus R things can be divided into 3 groups containing P, Q, R things respectively is P plus Q plus R factorial divided by P factorial into Q factorial into R factorial. So it is basically this case. Total 10 chocolates divided into 3 groups of 2 chocolates, 3 chocolates and 5 chocolates. The number of ways of dividing 3 P things into 3 equal groups of P each. So when none of the 2 groups are identical, so out of 3 groups, no 2 groups are identical, so that means all the groups have distinct identities, then the number of ways is 3P factorial divided by P factorial into P factorial into P factorial, which is P factorial Q. But if the 3 groups are identical, in that case the number of ways will be 3P factorial divided by P factorial into P factorial into P factorial, and 3 factorial will also get multiplied in the denominator because the 3 groups are identical. Okay. So we don't have to consider the arrangement of the 3 groups. So we'll have to divide by 3 factorial. Fine. So let's look at a question. Question number 6, first part, handout number 2128. So it says, in how many ways can 60 books be distributed among 5 students? So 60 books be distributed equally among 5 students. So each student should get 12 books. So 60 factorial divided by 12 factorial into 12 factorial into 12 factorial into 12 factorial into 12 factorial. Okay. So since we are dividing the parcels among 5 students, then these parcels will have distinct identities because it is being given to different kids. Okay. So this is the answer. Or you can do it this way, 60 factorial. So first we form the parcels by 12 factorial into 12 factorial into 12 factorial into 12 factorial into 12 factorial. So 5 times. But now we are only forming the parcels right now. So divide by 5 factorial also, because these are 5 lots, these are identical. And then when you distribute it among 5 students, then into 5 factorial. This 5 factorial is for distribution of parcels and this entire thing is for formation of parcels. So this 5 factorial will cancel out. So you will get the same answer which is written here. Fine. In how many ways can 60 books be divided equally into 5 unnamed parcels? So when you say unnamed parcels, it means these parcels do not have distinct identities. They are all identical. So the question gives you a clear-cut hint. Unnamed parcels means they are identical parcels. Okay. So what will be there in this case? 60 factorial. In this case we just have to do the formation of parcels, but these are unnamed parcels, so they are identical. So therefore you divide by 5 factorial also. So in this case 60 factorial by 12 factorial whole to the power 5, and this 5 factorial should also be multiplied. Fine. Okay, let's look at another example. This is an example. Distribute 12 different chocolates among 5 kids such that 3 kids get 2 chocolates each and 2 kids get 3 chocolates each. So what will be the required number of ways? 12 factorial, total number of chocolates, by 3 kids are getting 2 chocolates each. So 2 factorial into 2 factorial into 2 factorial, which is 2 factorial cube, and 2 kids are getting 3 chocolates each. So 3 factorial into 3 factorial, which is 3 factorial square. But these 3 chocolates, these 3 kids who are getting 2 chocolates each, these 3 lots of 2 chocolates will be identical. So divide by 3 factorial. And these 2 lots of 3 chocolates each, they will be identical. So divide by 2 factorial also. So this part is just formation of parcels. We have not given it to the kids right now. We have just formed the parcels. Now when you give it to the kids, next thing we multiply with the distribution of parcels. So there are 5 kids, so 5 factorial ways. So this entire thing will give the total number of ways in this case. Fine. I hope it is clear, the distinction between when you have to form the parcels and when you have to form the parcels and thereafter you have to distribute the parcels also. Alright. Now let us look at different types of distribution. So let's look at type 1. So we have done some basics on distribution. Now let's look at different types. So type 1 is when we have to distribute different balls into different boxes. Different balls into different boxes. And this is a case when a box can have 0 balls also. Okay. In this case a box can have 0 balls also. So it is not mandatory that every box should have at least 1 ball. It is possible that we do not distribute any ball to 1 box or more than 1 box. So example, distribute 5 different balls into 3 different boxes. Box can have 0 balls also. So these are the 3 boxes. Let's represent them by A, B, C. I have used different color for the 3 boxes. So let us say one box is A, another box is B, and the third box is C. These are 3 different boxes. So one way is we give all the 5 balls to one box. Okay. Now this 5 balls can go into A also, can go into B also, can go into C also. But right now we are not distributing, we are just forming the parcels. Okay. We are just forming the parcels and we are looking at possibilities. So if 2 boxes are empty, then all the 5 balls will get into the same box. Or we can have the case like this, 4, 1, 0. Or we can have 3, 2, 0. This is when one box is empty. So if one box is having 0, then the other 2 boxes can have 4, 1 or 3, 2. Now, we have taken care of the case where 2 boxes were empty and only 1 box was empty. Now, if no box is empty, then we can have 3, 1, 1 or 2, 2, 1. These are all the possible cases. Fine. So we'll have to look at all these possibilities because unlike the previous examples we did, here it is not specified that how many balls have to be put into the boxes. So we'll have to consider all possibilities, right? If it was already given that 2 balls have to be given to one box, another 2 to another box, and another 1 to the third box, then there would have been only one case, this one. But since it is not specified, we have to consider all possibilities. So these are all the 5 possibilities. All possibilities because number of balls to be put in the boxes is not specified. Fine. Now let us look at how we can distribute. Fine. So for this first case, total 5 balls are there. Now 5 balls have been distributed in lots of 5, 0 and 0. So 5 factorial by 5 factorial into 0 factorial into 0 factorial. This 2 factorial is because these 2 parcels are identical. So this much part is for formation of parcels, and when you multiply 3 factorial, this will be the distribution of parcels into the 3 different boxes. So there are 3 different boxes, that is why 3 factorial. So when you calculate this entire thing, you will get 3. Okay. Second case will be 5 factorial, total number of balls, divided by 4 factorial into 1 factorial into 0 factorial. And here all these 3 lots are different because they have different number of balls. So we do not have to divide by anything else here. And this 3 factorial is for distribution of parcels. Till here it is formation of parcel, and into 3 factorial is distribution of parcels, because there are 3 different boxes. So this will give you 30. Here we have 5 factorial by 3 factorial into 2 factorial into 0 factorial multiplied by 3 factorial. Why? Because distribution of parcels. That will give you 60. In this case we have 5 factorial by 3 factorial into 1 factorial into 1 factorial into 2 factorial. Here we have 2 factorial because these 2 lots will be identical. Okay. And when you distribute them into 3 boxes, then this is for distribution of parcels. Fine. And for the last case, we'll have 5 factorial divided by 2 factorial, 2 factorial, 1 factorial. These 2 are identical lots, so divide by 2 factorial also, and multiply by 3 factorial for distribution of parcels. So if you add all these cases, 3 plus 30 plus 60 plus 60 plus 90, we are going to get 243 ways. Fine. Okay. Now for this type, different balls into different boxes, we do not have to do it this way. It can be done in this way, but here we are making cases and then solving. Easy way out is, this question can also be done by looking at number of choices for each ball. So this is something similar to what we have already done while counting things in fundamental rule of counting and examples based on them. So these are my 5 balls, B1, B2, B3, B4, B5. First ball can be put into any of the 3 boxes. So there are 3 ways. Second ball can be put into any of the 3 boxes, right? Because you can repeat the same box, right? Because it is not mandatory that the balls have to be put in every box. The boxes can be empty also, right? Second ball can get into the first box again. Okay. So for the second ball, we again have 3 choices. And similarly for the third ball, we can repeat the same box. So again 3 choices, again 3 choices, again 3 choices. So it is 3 to the power 5, which is nothing but 243 ways. Fine. So in this case, we'll have 243 ways. This type of examples we have already done previously also. So such type of distribution question can be easily done by this method. Fine. So distributing n different balls into r different boxes, where boxes can be empty, the important is boxes can be empty, then it is r to the power n ways. Okay. So number of boxes raised to the power number of balls. These many ways will be there. Fine. Okay. So let's look at additional question from handout number 2128. Additional question 1, first part. There are 4 letters and 3 letter boxes in which the letters are to be posted. Find the number of ways of doing it if all the letters are non-identical and the boxes are non-identical. When you say non-identical, means they are distinct or different. So we have 4 letters and 3 letter boxes. So here n is 4 and letter boxes are the boxes basically. So this is R and this is N. So find the number of ways of doing it if all the letters are non-identical and the boxes are non-identical. And since the question does not specify whether the letter boxes can be empty or not, we'll assume that it is possible that one or more letter box is empty, right? Anyways, it is a question on letters and letter boxes, so it is not necessary that all the letters have to be posted into different letter boxes. You can post all the letters into the same box. You can maybe use only 2 letter boxes for posting the letters. You can use all 3 of them. So all possible choices are available to us, right? So what is the answer? Since letter box are distinct, so each letter can be posted in 3 ways. So 4 letters can be posted in 3 into 3 into 3 into 3. Each letter will have 4 choices. So 3 into 3 into 3 into 3 will have 3 to the power 4 ways. Fine. Okay, let's look at this question. This is question number 2. Question number 1 has other parts also that we'll see later. Let's look at question number 2 of additional question from 2128. Find the number of positive integral solution of a into b into c equal to 385. This ABC is a into b into c. Okay, it's a product of ABC. So if you prime factorize this number 385, you will be getting 5 into 7 into 11. Okay, if you prime factorize this number, you will getting 5 into 7 into 11. So the required solution is same as 3 letters to be posted into 3 letter boxes, which can happen in 3 into 3 into 3 or 3 to the power 3, which is 27 ways, right? So how is this possible? So these are my letter boxes. So ABC, the values of ABC, these are my letter boxes, and 5, 7, 11, these are my letters. Okay. Now this 5 can go into any of the box A, B or C. Similarly, this 7 can go into any of the box A, B, C, and 11 can go into any of the box A, B, C. So I'll just show you a few examples. Suppose 5 goes here, 7 goes here, and 11 goes here. And then you do the product. So A into B into C is 5 into 7 into 11, which is 385. It is also possible that 5 and 7 both come into this box, 11 comes into this box, and the box which has nothing is basically the number 1. Okay. So 5 into 7 here into 11 into 1, that also gives you 385. Or it is possible that 5 is here, 7 is also here, and 11 is also here. And the other two boxes are empty, which means basically they are numbers 1 and 1 each. So again you multiply all of these numbers, you will again get 385. Fine. Or maybe you can have 11 and 5 here and 7 here, and the one box where we do not have anything, it is basically the number 1. So 7 into 11 into 5 into 1, that still gives you 385. So basically in this question, these three are my letters, and A, B, C, the variables in the question, these are my letter boxes. So the number of ways of putting these 3 different letters into 3 different letter boxes, that number is basically the number of positive integral solution for this equation. Fine. I hope it is clear. Okay then. So what we'll do is, we'll deal with the other types of distribution examples in the third part of this session. And I suggest you that you do a quick revision of what we have done in the distribution type 1 and the basics of distribution, so that you will be able to understand the other types easily.